Swayam Prabha. Digital India. Educated India.
So in this lecture, we will discuss about constraint molecular dynamics. In the last lecture itself, we discussed some of the motivation for doing constraint molecular dynamics. When we try to simulate a molecule, we recognize that there are intramolecular interactions and intramolecular interactions and also intermolecular interactions are present. So in the intramolecular interactions, we are talking about bond stretching, angle stretching, torsional rotations, etc. Whereas in the intermolecular interactions, we are talking about essentially non-bonded interactions, namely the Lennard-Jones, Coulombic interactions. So now, in principle, one can actually include all these interactions in simulating a molecular system. But we realize that if you look at the time scale of these processes, the angle stretching, bond stretching compared to the translational motion of the entire molecule's center of mass, we see that these are happening at a very low time scale. And these are happening at slightly at a larger time scales. So then your step size for the integration of equation of motion is limited by the fast movement of this bond stretching and angle stretching that basically limits the achieving long time simulations in the system. So one way to avoid this problem is to consider these bonds and angles as set of constraints rather than specifying the intramolecular interactions. So thereby what we can do is we don't have to have explicit functional form for the bond stretching and angle stretching. We can just keep them as a rigid bonds or rigid angles. And in the last example, we took water as an example, water molecule as an example, and then we showed that if I denote the this hydrogen atom as 1 and this oxygen atom as 2 and then this hydrogen atom as 3, we said that this particular bond length can be considered as a constraint, and similarly this OH bond length can also be considered as a constraint, and then this molecule is only allowed to translate and this bond angle is allowed to stretch. And then we wrote the equation of motion, and then we applied undetermined Lagrangian multipliers, so that this the rigid constraints that we are talking about basically offers an additional set of forces, constraint forces, so that at any point of time the molecules preserve the OH bonds in the system. And now we will actually build on this this particular idea. Water is we are taking water as an example because water is most of the simulations water acts as a solvent, and when we try to do simulation of a system in water, for example surfactant in water or a nanoparticle in a water, we are mostly interested in the behavior of the solute, and we are not so much worried about the effect of the solvent in principle. So we don't want to spend so much time, computational time on simulating water. So we treat all these water molecules into a set of rigid constraints. So what we can do is we can actually go beyond, and then we say that not only this bond lengths are constraints, we can even constrain the bond angle also. So this angle is actually fixed to a particular angle, so that this entire molecule acts as a rigid molecule. Okay, the structural integrity is maintained at all the time. The way to implement this would be, you can think of this H and H could have some virtual bond of certain length, and this length depends on the opening angle here at equilibrium. So in the original model of the full constrained water model would have two OH bonds and one HH virtual bond being constrained, And then we are going to look at how to implement these constraints in simulating water as an example. And the same idea could be extended to any large molecular system as well. Thereby we specify the number of constraints, and then for each of those constraints we determine set of undetermined the Lagrangian multipliers, and then we use any of this finite difference method such as Verlet algorithm or velocity Verlet algorithm, leapfrog algorithm. One of those algorithms can be used to update the positions. So now let us start with water as an example. And then here we are going to constrain. The constraints are two OH bond lengths are fixed, and the HOH bond angle or HOH angle is also fixed. So the meaning of fixing the HOH angle basically means we are talking about some virtual bond is fixed. So again we use the same nomenclature like before. We say the hydrogens are 1 and 3 and the oxygen is 2, and then we start writing set of equations. So first we write this Lagrangian equation of motion, in other words the Newtonian equation for each of this atom. So this double dot here basically is a second time derivative of position, so it is basically acceleration. So we basically write equation of motion for all the 3 species here, and this F here are the conservative forces coming through non-bonded interactions, and this G1, G2, G3, these are the additional constraint forces because of the fixed bond lengths. Now the constraints are going to be the following. The mathematical function for constraints here, DAB is basically the bond length or the equilibrium bond length of atoms A and B. Okay, so D12 is the bond length of OH, D23 is the bond length of the other OH, and D31 is basically the virtual bond length between H and H, which is determined by this equilibrium angle here. So we have got basically 3 constraints. So this 3,1 here, that is the bond length of this HH, and this R12, R23, R31 are basically the at any instant of time the distance between these atom pairs, and we basically want this function to be 0 at all times. So these are our constraint functions, and then with this if you recollect from the previous lecture, we can write the expression for the constraint forces using the Hamiltonian principle of constraint Hamiltonian. So we write this G I, where I can be 1, 2, 3. We write this as sum of forces here. So here lambda 1 2, lambda 2 3 and lambda 3 1. So these are the undetermined, that means we don't know what the values yet. These are undetermined Lagrangian multipliers. And these functions chi12, chi23, chi31 are the set of constraints that we have already defined. And here these are the derivatives with respect to the position of each of this atom Ri. So this Ri here is basically the position vector of species I. So remember, this I can be either 1 or 2 or 3. So we are able to write the set of constraint forces for each of these species as sum of the gradient of these constraint forces chi12, chi23 and chi31. So now what we can do is, now like we did before, we can substitute for the values of chi12, chi23, chi31 for each of these case, and then get an expression for G1, G2, G3. So G1, again this G1 is basically the constraint force on the first atom 1 is lambda 12 R12. So this is a vector. So this R12 is basically the distance between atom 1 and 2, and similarly this R31 is basically the vector connecting 3 and 1. Similarly, the G2 here is minus lambda 12 So basically the idea is that if you look at this equation of motion, I know F1, F2, F3, all this can be calculated at any point of time. But then in addition, if I also know G1, G2, G3, then this equation can be solved to get particle positions and velocities as a function of time. However, the expression G1, G2, G3 involves these Lagrangian parameters which we need to determine. Once we determine these variables or these parameters, then we can find G1, G2, G3, apply in the equation of motion and then integrate them. So now we have to decide what is the final difference method we want to use. So first we will apply the most simplest Verlet algorithm. So if you remember, the Verlet algorithm goes as this. The position at t plus delta t is given as 2 times the particle position at time t minus the particle position at the previous time step t minus delta t, and then force. So this is the expression. So now what we are going to do is we are going to apply. So this is the case without any constraint, without any constraint force. So now when you apply constraint, what happens is that this becomes, you will see an additional term in the acceleration. So this is the extra term that comes because of the constraint forces in the Verlet algorithm. So now what we can do is, if you relate, if you want to replace this entire term with this, we can simply write that Ri at t plus delta t can be written as the position updated without any constraint force, which is designated as this prime here, So, first we update the position as if there is no constraint, and then we correct for it using this additional constraint force. Again, we are writing for ith atom, you can write for 1, 2, 3 by substituting I is equal to 1, 2, 3. So, now we have the expression for GI here, and that can be substituted here, and then we can explicitly write the position for R1, R2, R3, etc. So, what we have done is, in this equation we have substituted for G1, G2, G3 from this set of equations, and then you basically get the position of the first hydrogen atom H1 here is obtained first by calculating the position without applying any constraint force, that is this term, and then we add the additional constraint force, which is written as a function of this Lagrangian multipliers lambda 1 to lambda 3 1, which we do not know yet. We need to determine those, and you can see that these constraint forces G1, G2, G3, all of them basically acts along the bond length R12, R31, etc., etc. So, in this particular molecule you can see that this G1 here is basically acting along this is a basically vectorial sum of R12 minus R31. So, these are the bond length R12 and R31 is basically a vectorial sum of G1. Similarly, G2, G3, all of them are basically a net sum of the forces acting along the bond lengths. So, now so we have got the positions here, and then now our next objective is to find out these constants lambda 1 2, lambda 2 3 and lambda 3 1. So, once we know these values, we can use these set of expression to update the positions of 1 2 3 etc. So, to do that what we are going to use is we are going to use this constraints, which basically says that at any point of time this distance R12 should be equal to the bond length, and similarly we can write for R23, R34, R31 etc. So, this is the constraint that we want to seek. At any time t or t plus delta t, the bond length should be equal to the equilibrium bond length. So, these are the constraints that we want to use. So, what we are going to do here is that we have the expression for individual position vector R1, R2, R3, and what we should be able to do is obtain the R12, the difference between R1 minus R2 and R2 minus R3 and R3 minus R1, after getting this these vectors, and then take the modulus of this vector, absolute values, and those values should be equal to the equilibrium bond lengths. So, that is a condition that we want to apply, And once we do that, the only unknown parameters in these conditions would be the Lagrangian multipliers, and then we can solve them to obtain them. So, let us write this expression for R12, R23 and R31. So, this R12 is basically obtained from this set of equations. R12 is defined as R1 minus R2. So, that is the difference between these two expressions. And remember, this is something we are calculating at t plus delta t, because we know all the new positions now. So, so now we got this R12, R23. I am putting an overbar in all these vectorial quantities, just to be careful that what we are writing is a positional vectors. And so then next thing is to take a square of these terms and then equate this to the equilibrium bond length. I am going to skip these steps because it is quite lengthy to write here. And ultimately what we should be able to write is, we should be able to write an equation, a matrix form of this kind, where this matrix A here would have all the linear terms in this equation, Okay, so what happens is that you once you take the square of this term and then equate to the bond length, and then you'll get an equation which is quadratic in lambda values. And so what we can do is we can take all the linear term to the left, and then keep all the constants and nonlinear terms to the right. That would be in this matrix Q, which is a 3 by 3 matrix in this case. And this matrix element of A is given by basically dot product of these R12, R23, R31, etc. And there are some coefficients A, B, C, which depends on the mass and the delta T that you take. So this has to be now solved iteratively because it's a quadratic equation in lambda. So what we can do is we first so first in step 1 we choose some initial values. So these initial values can be something like lambda. All this lambda can be taken to be 0 to start with, and then what we are going to do is we are going to calculate this matrix Q with this chosen values lambda using all the Rij prime at a t plus delta t as well as Rij at time t. So once we have this estimated value of Q, then we solve A lambda is equal to Q, and this will give a set of lambda values. And these lambda values need not be the accurate ones. So what we do is we circle back to, so once you get a new value of lambda, we go back to step 2 and then get a new estimate of Q, and then again come back and solve for a new set of lambda, and then you iterate over and over until the values of lambdas are converged. So once you get a converged values of lambda, so once lambda values have converged, then we basically go to updating the particle position once for all, which we discussed here. So this is a set of equation that we want to now get, where this position without constraint force already we know. Now we got a converged values of lambda 1, 2, lambda 3, 1, etc. And then we can substitute this and get a new position. So this particular algorithm where we apply constraint MD using a Verlet algorithm is actually popularly known as shake algorithm. Even though we have shown this application of shake algorithm for water molecules, this can be applied to any number of constraints in a polyatomic molecules. The only constraint there would be that when you solve this equation, in the case of water, this would be inverting a 3 by 3 matrix is required, and then when you have a very large number of molecule with a large number of constraints, at every time step over and over during this iterative process, we need to do this matrix inversion, which is quite expensive calculation to do. So instead, what we can do is we can actually approach this problem by taking one constraint at a time. First we optimize the Lagrangian parameters by constraining one constraint and then iterate over all the constraints. So such a generalized approach of applying constraint method is known as shake algorithm. So when you apply LAMS or any other software, you'll have a choice of which algorithm to be used for a constraint dynamics. And if you use a shake algorithm, is basically a constraint dynamics with Verlet as a integrator. So within this Verlet algorithm, if you want to get velocity, we can go ahead like the way we do before. We take the position at r plus delta t and then position at r minus delta t for every atom. So I can put I here. So we get the velocity of each species at time t and t plus delta t as well. So this is the method of shake algorithm. Now moving ahead, suppose what if you want to apply velocity Verlet algorithm or leapfrog algorithm. So the method remains the same. Only difference would be how we get the unconstrained and the constrained position updates. Only difference will come there. So let's apply constraint dynamics within velocity Verlet algorithm. and this method is actually popularly noted as a rattle algorithm. So when you apply an MD simulation using any open source, when you get a choice of a rattle or a shake, it basically refers to applying constraint dynamics with a particular finite difference method. So shake uses simple Verlet algorithm and rattle uses velocity Verlet algorithm. So let's see how we apply the velocity Verlet algorithm for a constraint dynamics. So to recollect, the velocity Verlet algorithm happens in 2 steps. The first thing is to update the particle position using the current velocities and positions and accelerations. And then what we do is, at the same time, we also get the velocity at half step using the current velocity plus the current force. And then once we have the new position, we can get new accelerations or new forces at t plus delta t. So once we calculate the new force, we can update the velocity using this expression. So this is basically the principles of velocity Verlet algorithm. It happens in 2 steps. The first step is to calculate the position and the half step velocity, and then using the new positions we get new forces. In the second step, we update the velocity at t plus delta t using this new forces. So now when you apply the constraint dynamics in this algorithm, so we basically start writing, again we are writing for some species I. So the same particle position without any constraint force first we calculate, the same way that we have discussed here using velocity Verlet algorithm, and then you have this additional force which is called the constraint force comes into picture. And similarly, the half step velocity is obtained by taking the velocity at half step without any constraint force, and then we add the constraint force. So now with this new position, we calculate new forces, and then we get the new velocity. So here you can see that this is the constraint force Gi at time t, but then now that we have got new position and new forces, so we have to accordingly change this constraint force, and I am denoting with the superscript v here because this is a new constraint force at a time t plus delta t. So now the question is, these Gi and Giv, these are all written in terms of undetermined Lagrangian multipliers. So to obtain these multipliers, what we are going to do is, we know that the bond lengths are constant, that is this Rij square is actually constant. Actually it is this is the constraint that we want to maintain, because all this Rij square should be equal to Dij square for all the pair 1, 2, 2, 3 and 3, 1. Now if you take a derivative of this, you can show that Rij dot Rij dot should be equal to 0, and we use this set of constraint to obtain the Lagrangian multiplier of these particular functions. So we get a new set of Lagrangian multiplier and then substitute it here and get a new velocities. So both new positions and new velocities are accordingly updated. So this particular algorithm, as I said before, is called rattle algorithm. And then if you look at GROMACS, it uses what is called this links, which is basically constrained dynamics with leapfrog integrator. So in many simulations, whenever you deal with the water or any other solvent, we usually constrain this bond lengths and bond angles and bonds of the solvent molecules, and you have a choice of constraining these bonds and angles using either shake or rattle or links. So these are the 3 algorithms that are available in many of the open source code MD simulations. And if you were to write your own code as well, so this is a way that you would write your code to update the particle positions and velocities.